Hello everyone. Today, I am going to show you all how to design a steam power cycle that can achieve a cycle thermal efficiency of at least 40% under the conditions that all turbines have isentropic efficiencies of 85%, and all pumps will have isentropic efficiencies of 60%. In our project-based learning question, we are going to choose one cycle from gas-vapor cycle, which is simple Brayton cycle, and another cycle will be chosen from the vapor power cycles, which is the Rankine reheat cycle, to make comparison. In our design, we have assigned the value for T1 equals 21.08 degrees Celsius, 294.08 Kelvin, and T3 equals 600 degrees Celsius, 873 Kelvin for both cases. We have proceeded with trial and errors method in order to obtain the most desired value for our design. For simple Brayton cycle, the value that involved in trial and errors is the value for pressure ratio, R. The value of R is then used for further calculations for T2 and T4 in order to obtain the thermal efficiency for the process. The figure shows the TS diagram for the simple Brayton cycle. Now we assume the constant specific heats at the room temperature Cp equal to 1.005 kJ per kilograms Kelvin and Cv equal to 0.718 kJ per kilograms Kelvin, and the K value is 1.4. By using R equal to 2, which mean P2 over P1, we use the following formula, and we will get the T2s equal to 358.49 Kelvin, and for T4s we will get 716.15 Kelvin. In order to get 60% of pump efficiency, we used the following calculation, and we will obtain 401.43 Kelvin for the T2a. And for the 85% turbine efficiency, we will obtain the value 739.86 Kelvin for the T4a. Then we calculate the Qin, which is Cp multiply with the subtraction between T3 and T2a. We will get 471.57 kJ per kilograms. For the Q out, we will obtain 447.83 kJ per kilograms. The work net is the difference between the Q in and the Q out, and we will get 23.74 kJ per kilograms. Now we can calculate the thermal efficiency. The formula is 1 minus Q out over Q in. From the formula, we will get 5.03% of thermal efficiency. Now this is the result. We use different value of pressure ratio and the subsequent output for T2, T4 in thermal efficiency. Based on the result obtained, we can conclude that the Brayton cycle is not suitable to be used if we would like to heat from 294.08 Kelvin to 873 Kelvin. As pressure ratio, R, increases, the work net drops below negative. The best efficiency the Brayton cycle can achieve for this parameter setting is by using pressure ratio close to 1 with efficiency around 0 to 5.51%. Now, we try to use Rankine reheat cycle. The figure shows TS diagram of Rankine reheat cycle. First, steam enter the first stage turbine at 9 megapascal 600 Kelvin and expands to 300 kilopascal. It is then heated to 600 Kelvin before entering second stage turbine, where it expands to condenser pressure of 2.5 kilopascal. At point 1, refer to the table of 5, pressure 2.5 kilopascal, H1 equals to 88.424 kJ per kilograms. V1 equals to 0.001002 meter cube per kilograms. At point 2, pressure equals to 9 megapascal. Work in equals to H2 minus H1. which is H2S minus H1 equals to V1 multiply with P2 minus P1. And we will get 97.439 kilojoule per kilograms for H2S. In order to calculate 60% of pump efficiency, we use the following equation, and we will get H2 equals to 103.45 kilojoule per kilograms. Now we look at point 3. The temperature is 600 degrees Celsius, which is much more higher than the saturated temperature. So it is superheated condition, refer to the table of 6. We will get H3 equals to 3,634.1 kilojoule per kilograms, and S3 equals to 6.9605 kilojoule per kilograms Kelvin. At point 4, S3 equals to S4S. The enthalpy at 300 kilopascal is 6.2501 kilojoule per kilograms Kelvin. Since S4S is less than Sg, there is equality. We use the formula below to calculate, and we will get 0.9941. Then we can calculate H4S and get 2,712.165 kilojoule per kilograms. In order to get 85% of turbine efficiency, H4 will be equals to 2,850.455 kilojoule per kilograms. At point 5, the pressure is 0.3 megapascal, and referring to table of 5, H5 equals to 3,704.8 kilojoule per kilograms, and S5 equals to 8.5915 kilojoule per kilograms Kelvin. As we can see, S5 equals to S6S, and S6S is less than S6. There is quality. The quality we calculate is 0.9939. Now we can calculate H6S, and we will get 2,524.47 kilojoule per kilograms. In order to get 85% turbine efficiency, H6 will be equal to 2,701.52 kilojoule per kilograms. After we get all the data, we can calculate the Qin and the Qout. Qin is subtraction between H3 and H2 plus subtraction between H5 and H4, and we will get 4,384.966 kilojoule per kilograms for Qout. H6 minus H1 will get 2,613.096 kilojoule per kilograms. After that we can calculate the work net, which is Qin minus Qout, and we will get 1,771.859 kilojoule per kilograms. Lastly, we calculate the thermal efficiency, and we get 40.41%. For conclusion, simple Brayton cycle is not suitable to be used as the model steam power cycle when we fix the value of T1 and T3 as our reference value. However, for Rankine reheat cycle, the thermal efficiency resulted can achieve the minimum requirement for the design. The thermal efficiency is around 40.41%, and this result eventually fulfill all the requirement for the design. Therefore, Rankine reheat cycle is more suitable as the model for our steam power cycle.